This app aims at explaining how ANOVA works. So it allows you to play with one-way ANOVA. And as you can see, it is a very busy app. It contains a lot of things, a lot of tables, a lot of plots, but we will take it gradually, eventually. So let's start with this one. Okay. What you see here, it's the original data that we are going to analyze. By default, when you run this app for the first time, or when you refresh your window with this app, you will see some predefined, nicely looking values. That's I made on purpose because I want to use these nicely looking values to show you how everything, all statistics in ANOVA are calculated. But then when we take a new sample, then it will be completely random sample. Okay. So what do we see here? We see outcomes of 15 runs of experiment. It's just a chemical reaction which ran at using three different catalysts: catalyst A, catalyst B, catalyst C. And what we measure, it's the yield. It's how much of end product we got in milligrams. And then you can see that when we ran catalyst A, in average we got 95 milligrams here. And then when we ran the reaction with catalyst B, we got 100 milligrams. Again, 5 different outcomes, and this is the average outcome. This is the average yield. And then when we ran this reaction with catalyst C, we got 5 different outcomes, and this is the average, right? So what you see here is that, for example, if we just compare the observed values, the observed means, you can see that the highest amount of the biggest yield we got was when we used catalyst C. It's by 10 milligrams larger than catalyst A, the average yield we got using catalyst A, and by 5 larger if we look at the catalyst B. Okay, so this is our sample. So it's 15 values, 15 results of 15 reactions ran using 3 different catalysts. Okay. Now look, the first step in this particular case is the following. I compute the total grand average of these 15 values. In this case, it's easy because I have equal amount of values in each group, then the average of all 15 values will be just average of these 3 average values. And since they are like nicely organized, it's just 5 in between. So it's this one, it's 100. So we have in average for all 15 runs, we have 100 milligrams as average outcome, as average yield. Okay. And then I subtract this average yield. Why I do that? Because ANOVA, it's analysis of variance. And you remember from statistics, variance, it's a sum of squared distances, how far the values are going from the mean. And so therefore, to make all calculations easier, I subtract mean from the beginning. So I don't have to do it later. I just subtract it. It's called, this operation is called unbiased data. So because it's something common, I remove this bias. And then this is the unbiased data in this table. So in this table, you can see it's more or less the same values, but now I just remove this grand average, so I remove this bias. Let's make sure that we indeed have, we didn't change the variation of the values. You can see this one is minus 15. What does it mean? It means it's a value by 15 milligrams smaller than the grand average. And if you take 100 minus 15, you will get 85, and this is exactly what we have here, right? And then you can also see that the average now, we have minus 5, 0, and 5. Again, what does it mean? 0 means it's the same as a grand average, so it's 100. 5 means by 5 milligrams larger than the grand average, and it's 105, exactly what we have here. And minus 5 means it's by 5 smaller than the grand average, and again, it's 95, exactly what we have here. So now let's concentrate on this. Again, this is the same data, but unbiased, so we remove the grand average. Now we can calculate, first of all, we can find out how many degrees of freedom we have. You remember how degrees of freedom, it's how many independent values we have. At the beginning, we had 15 independent values. What means independent? It means that if I take this, for example, if I remove this 85 and keep the other 14, I cannot compute 85 because they are independent. There is no relationship that brings all these values together. But now, because I computed average and subtracted average from these 15 values, now I don't have 15 independent values anymore because I can just take this 15, and then I can simply take a sum of these values, of all these values, except this 15, and I will get minus 15, because now the average of all these values is 0, and it means that they all sum up to 0. So it means that now we don't have 15 independent values anymore, we have 14, because every value depends on the other other 14 values, right? So this is why you can see in this table, it's 14 degrees of freedom. Now to compute variance, you remember variance, it's a ratio between sum of squared distances from the mean and the degrees of freedom. And since I already subtracted the mean from these values, I just need to take a sum of squared values, because I already have the distances, right? So it means that, for example, I take this one, it's minus 15, squared, it's 225, this is 100, this is 25, and this is 25, right? So this 2 gives me 50, and then I have 150, and then I have 225 plus 150, so it's 375. And then if I keep going and calculate also sum of these squared values, sum of these squared values, and take a sum of all 3 columns, I will get 1000. So this is a sum of squared values. Okay. And now I can compute the variance, which is called mean square, sometimes MS. And then it's simply 1000 divided by 14, and that's 71.4. So this is the total variance of all values in my data. So this is the squared distances between all the values and the grand average, okay, the average squared distance. Now you can also see a representation, a visual representation here. The box plots, they show the population these values came from. So you can see that the box plots are identical, which means that the populations are identical. They have the same mean and the same standard deviation. However, you can see that the points show a certain pattern, right? So you can see these points in average, they line higher than these points, and these points, they line higher than these points, right? So you can see that the spread of the points, the variance of these points is the same, but we have a difference in means, and that's what also we can see here, okay? So we have a difference in means for these particular points. Now, you remember that, first of all, the first step in ANOVA is after removing bias, is when we represent these values as a sum of two terms, the systematic part and the random part. The systematic part is just we substitute all values with the means, assuming that this is what we get if we don't have any randomness, any random variation, any random factors at all. So if we don't have any randomness, all values, all reaction outcomes, when we use a catalyst A, should end up with by 5 milligrams a smaller yield than the grand average. So 95, or in this case, it's minus 5, right? And similarly, when we run the reaction with catalyst B, it should give us the same yield as the grand average is 100, or in this case in 0, because there is no difference between 100 and the grand average. And then if we do this with C, we expect that we can have, in all these cases, the yield by 5 milligrams larger than grand average, right? So this is my systematic part. Let's think how many degrees of freedom we have here. You can see that we have 3 unique values, but they sum up to 0. So once again, it means that you have only 2 independent values here. The third value depends on the other 2, because it's 0 minus 5, and then minus 0, it will be 5, right? So we'll see that later for the random sample, it's also true. We have only 2 independent values, and it means that we have 2 degrees of freedom, right? Sum of squared values. In this case, it's easy. All these values squared will be zeros. Then we have 25, 6 times, it's 125. And then also minus 5 squared is also 25, 6 times, it's another 125. So we have 250 in total. It's a sum of squared values here. And then you remember that variance, it's a sum of squared values divided to degrees of freedom. So we simply take 250 divided to 2, and that gives us 125. Now the next, it's the residuals. And residuals, it's simply a difference between the original value and the mean. So minus 15 minus minus 5 gives you minus 10, and so on. So this is what is rest when we removed all the systematic variation of the values from the values, right? And again, first of all, we need to compute degrees of freedom, not compute, but derive the degrees of freedom. We know that we had 15 at the beginning, then we lost 1 when we unbiased data, so now it's 14. And look, here we also lose 2 degrees of freedom, because we compare the columns, we compare the groups, and we have 2 independent comparisons here. So it's 14 minus 2, it gives us 12. So we have 12 degrees of freedom for residuals. We have 12 independent values in the residuals, right? And then again, we compute sum of squared residuals. So we square every value here and take a sum. And that gives us 750, right? And then you can see already that 750, so this is the sum of square root values in residuals, plus 250, it's a sum of square root values in systematic part, gives you 1000. It's a total sum of square root values, right? So this is total, and then we split it into two parts. This is the systematic part, and this is the residuals. And then we can also compute the mean squares, the variance, simply by taking the ratio between sum of square root values and the degrees of freedom, so that gives us 62.5. Okay. Now we measure how big the ratio is between the variance, systematic variance, 125, and the random variance, the residual variance, it's 62.5. And again, you can see that it's 2, right? So this is 2 times larger than this one. Okay. And that's what you can see here as in this plot as a f value. So this is f value. F value, it's a ratio between systematic variance and the random variance. So in this case, the variance for systematic part is 2 times larger than the variance for the random part. Okay. We'll come back to this plot in a minute, but so far let's also look at this box plot. So you can see that the black points here, it's green points plus these reddish points, right? So here we have a systematic part, right? And this is the residuals. And you can see that in the residuals, the average is 0. And then if we compute standard deviation for the residuals, it should be standard deviation for every population. So now let's look at this one. So what we see here, this is the f value. And you remember that f value, it's a positive value if null hypothesis is true, and this is our null hypothesis, right? So all averages are the same, and in this case, the null hypothesis is true, right? This is how I made this app. If null hypothesis is true, the expected f value, the ideal f value is 0. Because if null hypothesis is true, in ideal case, all these values should be also 0, and then the systematic part, the variance for systematic part should be 0. But we live in a random world, and even this systematic part is also random. You remember that average values of your sample are also random numbers, right? So therefore, we have f value a little bit larger than 0. It's 2. And what you see here, it's a distribution of possible f values for the case if null hypothesis is true, and then for these degrees of freedom, if we have 2 degrees of freedom in systematic part, and 12 degrees of freedom in the random part. So this is how f values are distributed in this case. And you can see you can get 8, 9, 10, but it's almost unlikely. And you can see that most of the time the f value will be somewhere between maybe 0 and 3, maybe 0 and 4. So this is 2. And now we can compute a p-value. A p-value, it's a chance to get f value as extreme as our, or more extreme. So all these will be more extreme, assuming that null hypothesis is true. So it's simply this area on the right, and this is what we can see. In this case, it's 17.8%. So in this case, we cannot reject null hypothesis, right? This p-value is quite large, so it does not contradict with our null hypothesis. So therefore, we do not reject null hypothesis, and we have no rejections here, right? So this shows you the amount of rejections, how many samples we got with null hypothesis being rejected. And then we work with significance level 0.05 here, right? So this is how it works. Now look at this part. What you can change here. You can change how far the average of first sample of group A goes from the ground average. So in this case, you can see it's 0. It's for population. This is how far the average of B goes from the ground average is 0. And then you can see here. So this is 0. So it means that the average values for all groups, for all 3 groups, are 100. This is the ground average that we have. Okay. You can also change noise. It's a spread. Again, it's a standard deviation for the population. In this case, it's 10 milligrams, right? Let's keep it as is, and let's take a new sample. So I take a new sample. Now it's a random sample. You can see that these values are not nice anymore. This is the this is the ground average. I expect to see 100 here, and for population, ground average is 100, but now it's much smaller, you can see. But if you look at these values and compare all these mean squares and so on and so forth, you can see that, for example, in this case, you have a small trend like this one is a little bit larger than this and this, right? Although we know that null hypothesis is true in this case, this is what we said here, right? But if you compute if you do all the computations, for example, you can see mean squares is very small. The mean squares for systematic part is very small. Mean squares for random part is quite large. So the f value is very, very small, 0.2. So This does not contradict with our null hypothesis, so we didn't actually reject in this case. And then if we keep going, you can see that when we have different samples, we may have, for example, this one looks pretty much as our initial example, right? So every next is a little bit larger. But this is the observed effect, and it can be random, we know. So this is why we need tests, to see how likely we can see this observed effect, or maybe even larger, although the null hypothesis is true. And then you can see the p-value, it's 57%, which means that it's quite likely. So there is no contradiction with null hypothesis, right? And then if we keep going, for example, in this case, you can see that I got f value pretty large. By chance, just by chance, we know that null hypothesis is true. This is the way I made this app, right? But you can see how big the difference, the observed effect is. So this is the observed effect. Between A and B, you have a very big difference, a bit smaller here, right? And then if you compute, you can see this is 300, this is 51. So this one is almost 6 times larger than this one. And that results with quite extreme f value. It is still possible to get a value like this. It is still possible to get 6, but the chance is very small. It's 1.7%. And since we work with 5% significance level, we reject null hypothesis here. But this is wrong. This is error. So once again, the meaning of this 0.005, it means that you have 5% chance to make a type 1 error, which means that you will reject null hypothesis. You will claim that catalyst in this case have an effect, so there is a difference between the yield if you use different catalyst, but in fact it's wrong, because we know that this is the truth in this case, right? So therefore, if you want to avoid if you want to decrease the probability of making this type of mistake, claiming an effect, although the effect is not present, you need to decrease the significance level, okay? So in this case, you can see I reject null hypothesis. So far, 14.3% cases where my null hypothesis was rejected, although it was true. But if I keep going, if I take a lot of samples, you can see that this value will be pretty close to 5%, especially if I take like thousands of samples. You will see that this value will be pretty close to 5%, because that's exactly how we made the test, right? So we work with significance level of 5%, and therefore the number of rejections will be approximately 5%, right? So in this case, I have 7, but if I keep going and have, for example, thousands of cases, then it will be 5%. So the meaning of this is exactly in significance level, right? So it means that if you take only one sample, you have 5% chance to make this error. Okay. It's very similar to what we have also in the t-test. Now let's see if we can actually observe an effect with ANOVA, right? So let me change this. And let's say I have only effect of -10, and it's only for A. So it means that when I ran the reaction using catalyst A, I have, in average, I have by 10 milligrams smaller outcome, smaller yield than if I use B and C. And you can see that there is no difference in B and C. It's only A that has a difference. Only one group is different. Okay. I keep all other parameters the same. And then if I start taking a new sample, you can see that approximately in 20, maybe 25%, I will see this effect. So this effect is quite small. You can see that it's only one group which is different, and the difference is comparing with one standard deviation, and that gives a power approximately 20, maybe 25% power. So almost 25% chance that I will be able to reject null hypothesis, which is wrong in this case. I know this is how I said it, and that's the power of ANOVA in this case. If I make it bigger, so for example, if I also say that the C gives you the highest yield, the highest outcome in average, so it means that the difference between C and A will be 20 milligrams. Then let me just click here to fix it. And then if, in this case, if I start, taking a lot of samples, you can see that the power is quite high. It's approximately 70%. So I have 70% chance to observe this effect, to reject null hypothesis in this case, if the effect is that big. Okay. And then you can see, again, the box plot shows you the reality, it's the population. And then you can see, for example, in this case, the observed effect is quite small than the expected effect, right? So this is why in this case I failed the reject null hypothesis. But if I take, for example, this sample, now you can see, although the effect should be like this, you can see this contradicts with my effect, right? But in general, this difference is quite large, so therefore I was able to reject null hypothesis because the p-value is approximately 3%. So this is how ANOVA works. So once again, ANOVA allows you to test only one thing. If you have any difference in groups, so it means that if you have at least one group which is different from the others. It doesn't tell you how big the difference is. It doesn't tell you which group is different. That's why you didn't need to use a post hoc test, for example, Toki test. But for answering this question, for testing for difference among several groups or among several factors, ANOVA is pretty good.